Hi and welcome back to 90 Day Dental Day 48. So we started off a two-parter yesterday on dental materials with the modern progresses that are being made, and today we're going to finish that off. So Will Palin is going to round that off for us.
Of course, material properties and the composition of these materials are very important for their success, but equally as important is consideration of curing the material, so polymerisation of the monomers, and how effective that process is, because this stage will significantly influence the properties of the set material. So we talk about things like degree of conversion, so the amount of polymer that is converted to polymer, the amount of cross-linking of the resins themselves. How far light penetrates through the material is also very important, because that in turn affects the amount of conversion at depth. And what should be avoided at all costs is undercuring throughout the depth of the restorative material. Inevitably, these materials will shrink, and that shrinkage can cause the generation of stress at the interface between the resin composite, the adhesive, and the dental tissue itself. And if that stress exceeds the bond strength of the adhesive that you've put down, then inevitably you're going to get gaps, which can cause secondary infection, secondary caries, and failure of the restoration. The more cross-linking you have, the more effective the material is cured, then the higher the mechanical properties are going to be. So it's very important to optimize this stage in order to get the most out of the strength characteristics and stiffness of the material itself. Undercuring also may lead to the higher presence of residual monomer, and in time, as the material absorbs water, that can leach out from the surface of the material. And again, it's controversial as to whether this really causes any unwanted biological effect, because the release rates are so small, and will be so small if the material is cured effectively. So why do these materials suffer from low depths of cure? Well, this diagram represents what happens to light. So as you cure the material, quite a lot of light is lost through reflectance and other optical effects like fluorescence from the surface or near to the surface of the material. As light travels through the composite, it is scattered by the filler particles themselves, and a big loss of light through the bulk of the material is absorption by the photoinitiator, obviously, because it needs to absorb light to generate the reactive species that cause polymerization, but also the pigments that are used. So the darker the color of the material, the more light is absorbed, and the lower depth of cure you might expect. Ignore this very fancy equation. If you are interested, this is known as Beer-Lambert's law and just explains how intensity reduces through the bulk of the material dependent on what is absorbing and how deep the material is. Oh, and I should also mention that we have optical properties of the material that can increase or decrease the amount of scattering. So refractive index refers to how quickly light is traveling through a particular medium. So as it reaches an interface, or as it travels from one medium to another, it may well slow down or speed up, and dependent on the properties of the two parts, so in this case the filler and the resin, if there is a big mismatch in density and light travels at different speeds at that interface, then it will scatter more. And again, manufacturers will optimize translucency of the material by adjusting the type of filler and sometimes the type of resin in order to maximize the amount of light that travels through the material. So this is a crude test of identifying how depth of cure varies in different thicknesses of material. So in this case, the hardness is measured down the cross section of a cylinder of material, and you can see there's an exponential drop off in hardness as we exceed approximately 2 millimeters for a conventional composite in a standard shade, probably A2. There has been an increase in popularity now of the use of so-called bulk fill materials. So we go from only being able to lay down about 2 millimeter increments to increments of around 4 or 5 millimeters. These are not necessarily significantly different to conventional materials, other than pigment has been, or most of the pigment has been removed from the resin composite itself. So they become a more translucent material, which enables more light to travel through the bulk in order to cross-link in deeper layers. That said, there has been some really quite innovative developments in terms of controlling the amount of shrinkage or shrinkage stress in higher volume materials. But more or less, they still use the same dimethacrylate chemistry that I mentioned previously, and they allow more light to travel through the material in order for you to use less increments and essentially save time. So, light curing, the properties of the light are also very important. So this figure here represents, the yellow line represents the absorption of the commonly used photoinitiator camphorquinone, and as you can see, it's this canary yellow dye. So its maximum absorption is around 470 nanometers, and this is why we use blue light. And although I don't think you can buy halogen lights anymore, some of you may still use these types of light curing devices, which is absolutely fine as long as the output is high enough. So essentially these are white light. This is white light that is filtered. So we use a bandpass filter to get rid of all the unwanted wavelengths, and it then corresponds with a maximum output at about 470 nanometers, i.e. blue light. And this interacts with the photoinitiator to initiate polymerisation. And more recently, well, over the last 20 years, we have kind of superseded halogen lights with the use of LED technology. So most dental curing units now, the light source is a diode centered around, again, the maximum absorption of camphorquinone. So this makes curing a lot more efficient. These are battery operated. We're not wasting energy by filtering out most of the light as we do in these halogen lights. So they can be more ergonomic and they can be battery operated and so forth. So a big step change in the way that dentists cure their resin composite materials. The disadvantage with camphorquinone, especially for those of you that are into high aesthetic restorative dentistry, is that not always does the yellow pigment disappear in the material. So you're left with a slight yellow hue, which is okay in most circumstances. But if you are layering composites and you require translucent shades without much pigment, or patients desire very bright white shades, then these types of materials can be problematic. So some manufacturers will reduce the amount of camphorquinone, the yellow pigment, and use alternative photoinitiators. So this white absorption curve shows the absorption of a photoinitiator known as MAPO. It's a phosphine oxide, and you can see that it absorbs light at much shorter wavelengths. It can also improve the efficiency of cure as well, but we won't go into that right now. So this can be problematic because if you look at the overlap, well, there is no overlap between the blue LED and the absorption characteristics of the white initiator. So it's not often that manufacturers will use the white initiator alone, so it's normally okay, but you will see, and some of you may have or own and use, LED lights that have multiple diodes. So you can see here that not only are their diodes centered around 470 and maybe a little bit shorter, but also back down at the 405. So these are designed to cure all types of materials that have the presence of alternative initiators. So it really is kind of replicating what old halogen lights used to be. But because LEDs are so much more efficient and so much easier to use, that far outweighs the output of quartz tungsten halogen lights. So some advice on how you ensure the best possible cure related to the material and the light that you own. You need to make sure that you have adequate light irradiance. So irradiance is the power output divided by the unit area that you're curing over. And if you take some ballpark figures, then modern LED lights probably have around 1000 milliwatts per centimetre squared. You can get lower intensity lights. Manufacturers do purport very high powered outputs. I've seen them even up to about 5000 milliwatts per centimetre squared, which is an awful lot of power. And you can use these, but I would issue a word of warning in terms of potentially how much temperature they generate. A good way to check that is just to put your finger over the curing unit and see how long you can keep it there. Because if it gets so hot, you don't want to risk pulpar injury or even burning mucosa, which I've heard of in some instances. It is actually quite difficult to know the output of your light unless you have appropriate devices to do so. There are some units that have a small detector on the side which will give you a relative measurement over time to see if it's decreasing. If you think you have a light that is underperforming or has a lower power output, can you compensate? Well, yes you can, because exposure time is the most important aspect of effective polymerisation. So you can actually, well, there's a shared relationship, a reciprocal relationship between irradiance and time. So if you have say an irradiance of 500 milliwatts per centimetre squared, you can double the exposure time and have an equivalent cure as a light that has double the output for half the time. So the product of irradiance and time is known as radiant exposure. And again, there's a rule of thumb that approximately 20 joules per centimetre squared will provide adequate cure of a conventional material with a conventional shade at 2 millimeters. Obviously, with bulk filled materials, these can be cured to higher depths, usually for the same amount of irradiance or radiant exposure energy that you deliver to the material. Other factors that will affect the extent of cure will be how far away the tip of your curing unit is to the surface of the material. So it might be important to compensate for that by stabilising the light as best you can and maybe increasing the exposure time if you know that there is a big tip to material distance. In relation to how much time you spend curing, obviously there are limitations. You can't over cure the material. However, what you want to avoid is excessive increase in temperature for the same reasons that I described with the risk of pulpal injury. Finally, just to touch on the problems associated with shrinkage. So as the material cures, it becomes more and more dense as cross-linking increases. So there comes a point in the polymerisation of the material where the flow of the composite can no longer relieve the stresses that are being built up as a result of the shrinkage. So this is known as the gel point. So it occurs late on in the polymerisation of these materials. So once the material loses its ability to have any flow that compensates the shrinkage that's happening, then that energy has to go somewhere. So it will be transferred to the adhesive at the cavity wall and will pull inwards. And as I said previously, if the amount of stress exceeds the bond strength, then inevitably you will end up with gaps, which increases the likelihood of bacterial invasion and secondary infection. It's worth pointing out as well that it's not only about shrinkage. So you may have a material that shrinks more but could actually generate less stress. Its stress is not an intrinsic material property. It's a complex interaction of many different factors, which includes the speed of cure, the modulus of the material, the configuration factor, so how many bonded surfaces you have, being that if you have more bonded surface, then you might expect more stress that's generated, and compliance of your tissue, so compliance of the tooth itself. So if a tooth can flex a little bit, then that'll actually reduce the amount of stress that is generated. So in summary, resin composites are incredible materials, really. They're hugely versatile. They have a very high use in dentistry for very good reason. They provide excellent cosmetic properties. You don't have to mix the material, it's a single paste. You have control over the setting reaction. So you have this spatial and temporal control by light activation. And of course, we've had it for quite a while, and it's clinically proven. There are some disadvantages, including technique sensitivity, so they are more complex to place than a silver amalgam, and then also the issues with effective adhesive application. You have the possibility of stress generation on setting, which can cause interfacial gaps. Limited cure depth, although that is somewhat overcome by the introduction of bulk fill materials, which then also improves the amount or decreases the amount of time that is required to place these materials, which I think on average is about 4 times that of a silver amalgam. Some of the mechanical properties have been improved vastly over the last few decades, and they do compare very well with most restorative materials, or certainly silver amalgam. However, it might be argued that they are slightly less tough materials. And of course, they are less karyostatic than silver amalgam, so they may be susceptible to failure in high caries risk patients. Resin composites are certainly the future of aesthetic restorative dentistry, and in future summaries, podcasts, I hope to go on to give you some more information about what's happening in terms of emerging technologies. And if you have any questions about resin composites or dental materials in general, then please do drop me a line at my email address there in the bottom left hand corner. I'll be happy to try and help in any way that I can. I fear that I've gone way over 10 minutes, but there you go. Hope you enjoyed, and thanks for listening.
And that was a superb session by Will, and really like to thank him for all his efforts and all his time that he's given us over the last couple of days to really update us on all these topics. And tomorrow we kick off with another one. See you then.